In this video, we'll discuss the process of verifying or proving trigonometric identities. Recall that an identity is an equation that is true for all possible values of the associated variables. To verify an identity, we must show that, in every possible case, the expression on one side of the equation equals the expression on the other side. We give a general process, followed by 4 specific examples to illustrate. In general, it's helpful to start with the expression on the more complicated side of the equation. Then look for opportunities to simplify factor expressions, add fractions, expand products, or to otherwise algebraically manipulate the expression with the goal of rewriting it to match the other side. Look for opportunities to use other known identities or to make helpful substitutions. If all else fails, it's often helpful to convert all trig terms to sines and/or cosines. Let's illustrate these steps with some examples. First, let's prove that tangent theta times cosine theta equals sine theta. For our solution, we'll start with one side. The product tangent theta times cosine theta is the more complicated of the two expressions. We replace tangent theta by the ratio sine theta over cosine theta. Next, we use a fraction multiplication property to rewrite the product. Then replace cosine theta over cosine theta by 1, and we get sine theta. Therefore, we have established the desired identity. Let's consider a second example. This time, let's prove that the product of 1 plus sine x times 1 plus sine of negative x equals cosine squared x. We will again start with the more complicated expression and use the fact that sine is an odd function and replace sine of minus x with minus sine x. Then we can expand the product using the difference of squares property. And finally use the Pythagorean identity to rewrite 1 minus sine squared theta as cosine squared theta. Therefore, we have again established the desired identity. Let's now consider a problem with a couple of different avenues for attack. Let's prove that the quotient secant squared theta minus 1 over secant squared theta is equal to sine squared theta. Some people would immediately jump in and change everything to sines and cosines, but there are better alternatives if we think a minute. The more complicated expression is on the left-hand side of the equation. One option is to unadd the fractions since the denominator has a single term. Notice that adding the fractions on the right-hand side does indeed produce the original expression. Now we can replace secant squared theta over secant squared theta with 1, and the reciprocal of secant squared theta with cosine squared theta. Finally, the Pythagorean identity gives us that 1 minus cosine squared theta equals sine squared theta. And therefore, we have established the desired identity. Let's rework the same problem using a different route. The left-hand side still contains the more complicated expression. This time, though, let's use the Pythagorean identity to substitute secant squared theta minus 1 equal tangent squared theta. Recall that this form of the Pythagorean identity comes from dividing both sides of sine squared plus cosine squared equal 1 by cosine squared. Now we separate into a product of two fractions. Then replace tangent squared theta with sine squared theta over cosine squared theta and the reciprocal of secant squared with cosine squared theta. Cancel your cosine squared thetas and you get sine squared theta. So again, we have established our desired identity, but we've used slightly different steps. For our last example, let's consider a problem in which we factor trigonometric expressions. We want to prove an identity with fractions on both sides of the equation. Note that we won't assume equality and cross multiply because we can't assume equality. We're trying to establish equality of these two expressions. We will still start with only one side and show that it equals the other side. The left-hand side seems a little more complicated since the denominator has multiple terms. So we start with the left-hand side, and we can factor a tangent theta out of the denominator. We notice that the numerator also factors as the difference of squares. Now we can rewrite this expression as a product of two fractions and reduce as appropriate. Therefore, we get the desired identity. We should note that proving or verifying identities definitely takes some practice and many false starts. It's important to be both patient and persistent when attempting these problems.